All right, welcome to The Explainer. Today we're going to get into something really fascinating. How does an AI figure things out when it has no map, no clues, basically when it's exploring completely blind?
Seriously, just picture this for a second. You're dropped into a huge maze. The exit is hidden somewhere inside. You don't have a map. What do? Do you just pick a wall and follow it? Try every single corridor methodically? The kinds of strategies you'd probably come up with? Well, that's exactly what we're looking at today for an AI agent.
So here's our game plan. First, we'll lay out the problem our blind explorer is up against. Then, we'll meet two very different kinds of explorers, one that plays it safe and wide, and another that dives in deep and fast. After that, we'll see how to patch up a search strategy that can get itself lost, and we'll ask what happens when not all steps are created equal. We'll wrap it up with a guide to picking the right strategy, and finally, look at just how powerful these simple searches can be.
Okay, let's get right into it. What exactly is the challenge our so-called blind explorer is trying to solve?
At the heart of all this is what we call a problem-solving agent. You can think of this as our AI explorer. All we do is give it a starting point, the initial state, a finish line, the goal state, and a rule book of legal moves it can make, like turn left or drive to the next town. The agent's whole job is to figure out a sequence of those moves to get from A to B.
And this is the kicker. The key term here is uninformed or blind. It means our little explorer is working with zero extra hints. It can't tell if it's getting warmer or colder as it gets closer to the goal. It can't see the finish line off in the distance. The only things it knows are where am I right now and what moves can I legally make from here. That's it. It has to find the solution just by trying things out one by one.
So this leads us to two fundamental strategies our blind explorer can use. And honestly, it's kind of like they have two totally different personalities. One's really cautious, and the other's a bit of a daredevil.
First up, let's talk about the cautious one, breadth first search, or BFS for short. Imagine you're in a big hotel looking for a friend's room. Using BFS would be like checking every single door on your floor first before even thinking about going to the next floor up or down. It's methodical, it's thorough, and it explores everything one level at a time.
You see, the process is super systematic. You start at the beginning, what we call the root, then you check every single possibility that's just one step away. Once you've checked all of those, only then do you move on to explore everything that's 2 steps away. It creates this ever-widening ripple effect, which guarantees that when it finds the solution, it will be the one with the fewest possible steps.
And then, on the complete other end of the spectrum, you have our reckless explorer, depth first search, or DFS. This one's the polar opposite. It just picks a path and goes for it, diving down as far and as fast as it can. It doesn't look left or right. The only time it reconsiders is when it smacks into a dead end. Then it backtracks just enough to try the next deepest route.
So you can totally see the difference, right? It's not that widening ripple, it's more like a deep, focused dive. Pick a direction and just go until you can't go any further. Then you pop back up, find the next turn, and dive down again. It's way faster and uses a lot less memory because it doesn't have to remember all the paths it didn't take.
Okay, so this is where it gets really interesting. It's all about the trade-offs. BFS, our cautious friend, is complete, which just means it's guaranteed to find an answer if one exists. And it's optimal, meaning it'll find the shortest one. But the downside is a monster. It chews through memory like crazy. DFS, the reckless one, is super fast and light on memory, which is awesome. But, and it's a big but, it's not complete. It can literally get stuck in a loop forever. And it's definitely not optimal. The path it finds is often not the best one.
So that leads to a pretty obvious question, right? DFS is amazingly fast and efficient with memory, but the fact that it can just get lost forever is a huge problem. So how do we fix that?
Well, the first kind of simple fix is something called depth-limited search, or DLS. And it's exactly what it sounds like. It's just regular old depth-first search, but we put a leash on it. We tell it, hey, you can go deep, but you are not allowed to go deeper than this specific limit. It's like a safety harness that stops it from wandering off into an infinite abyss. So let's just say we set that depth limit. We'll call it L to 3. Our agent goes on its usual deep dive, but now it has this new rule. The moment it gets 3 steps away from where it started, it has to stop. It has to treat that point like a dead end,
even if the path could actually go on. And right away, you can see the huge flaw, can't you? What happens if we cleverly set our limit to 3, but the actual, real solution was just one step further, at depth 4? Well, DLS would give up and never find it. We fixed the infinite loop problem, but now we've got a new one. We might accidentally cut ourselves off from the answer. And that brings us to a really, really smart solution: iterative deepening search, or IDS. This strategy is just brilliant. It says, okay, let's run a depth-limited search with a limit of 0. If it finds nothing, fine. Try again with a limit of 1. Still nothing. Try again with 2, then 3, and so on. It keeps increasing the depth until it finds the goal. You get the best of both worlds, the tiny memory footprint of DFS, with the guaranteed success and shortest path answer of BFS. It's pretty awesome.
Okay, so up until now, we've been pretending every step is equal. One move is just as good as another. But what happens when we throw a wrench in the works? What if some moves are more expensive than others?
I mean, this is super important for something like planning a road trip. A path with 2 short city-to-city hops might be way better than a path with just 1 super long hop. Breadth-first search doesn't care about that. It only counts the number of hops. It would see the 2-hop path as worse than the 1-hop path, even if it's a shorter total distance. That's not what we want if we're trying to save on gas.
So for this, we bring in the Economical Explorer, Uniform Cost Search, or UCS. This algorithm completely ignores how many steps it's taking. Instead, what it does is, it always looks at all the paths as started and asks, which one is the cheapest so far? It keeps a running total of the cost for every path, and it always chooses to explore the one with the lowest price tag, which guarantees it finds the cheapest overall solution.
Phew, okay. We've thrown a lot of acronyms at you. BFS, DFS, IDS, UCS. So let's pull it all together. Think of this next part as your ultimate cheat sheet for picking the right explorer for the job. All right, let's break this chart down. Complete just means, will it always find an answer? You can see BFS, IDS, and UCS get a big yes. Optimal means, will it find the best answer? Again, same 3 winners. But now look at the columns for time and space, how long it'll take and how much memory it needs. This is where things get real. That weird notation, O, B to the D, B is just how many choices you have at each step, and D is how deep the answer is. For BFS, both time and space grow exponentially, which makes it totally unusable for big problems. DFS is fantastic on space, but it's not complete or optimal. And this is why everyone loves iterative deepening, IDS. It gets the yes for complete and optimal, just like BFS, but with the amazing memory savings of DFS. It's a real star.
Now, it might seem like all these blind strategies are, well, a bit basic, right? But understanding why they work, and more importantly where they fail, is totally key to building smarter AI.
So what does that crazy exponential complexity we talked about actually feel like? There's this amazing example. For a pretty modest problem, say with an answer 12 steps deep, BFS might find it in about 13 days. Okay, long, but you could wait. But here's the absolute killer part. The memory it would need to do that is 1 petabyte. Your computer doesn't have a petabyte of memory. No personal computer does. And that's the real difference between something being theoretically possible and actually doable.
These uninformed searches are the foundation, the absolute bedrock of AI problem solving. They show us the incredible power and the stark limitations of just exploring systematically. And all of this really sets up the big question, the one we'll get into next time. If this is what an AI can do when it's completely blind, what happens when we let it see? What happens when we give it a hint, a sense of direction? Well, that's when things get really interesting. Thanks for watching.